One camera. Yeah. Hello students, welcome to IMS GATE Academy. In the last few sessions, we have covered a lot many things about deterministic finite state automata, and we understood how to make DFAs. Now, what is the problem is, see, what can happen at the runtime that the DFA that we have made is not minimal. We have to check that whether the DFA that we have got is minimal or not. That is what the next thing is, right? So, so let's see through an example and try to understand this idea, right? So although just to brief you guys, what we have discussed till now is we have seen what is finite automata. We have seen why we study the subject of theory of computation. We have seen what are the applications of theory of computation, and then we started with deterministic finite state automata. We discussed that what does it exactly mean when we say deterministic finite state automata. We discussed the tuple, the quintuple of the deterministic finite state automata, that is Q, sigma, delta, Q naught, and F. We have discussed that in detail, and now what we will do today is, hi Ravi, hi. Is my voice and video completely fine? Yeah. Okay. Okay, great. Thanks, Ravi, for confirming. Right. So what we have done is we have talked about the various about the quintuple of the deterministic finite state automata, and then we did some 10 to 15 examples on DFAs to understand and get in hand on the DFA so that we can make any DFA that comes in the exam. But now what might happen that the DFA that we have made is not the minimized DFA. Now, what do we mean by the minimal DFA? Minimal DFA means that what you have got is not minimal. That means the number of states can be reduced further, right? So that means what do I actually mean by this? That when we have, say for example, the DFA that you made is having some 5 states. Now what might happen is it can be reduced to 4 states. It can be reduced to 3 states. And we want to get the minimal DFA. That means that what does the term minimal mean? Minimal mean, yeah. Hi Hemkumar. Yeah. So when I say minimal DFA, what does this term minimal mean? Minimal simply means that the number of states cannot be reduced any further. You will have at least this much state in your DFA. You cannot make a DFA which will have lesser number of states than this DFA. Therefore, we get a minimal DFA. So now there might be situations where we do not get in the first go the minimal DFA. We do have an approach called minimization approach through which we can minimize the DFA that we have got. Right? So let us take an example where I will show you. Let us take a few examples on DFAs again. Then I'll give you the motivation for minimizing the DFA, and then we will discuss the minimization approach for the DFAs. Right? So that's roughly the agenda of this session. We will do 1 or 2 questions again on DFAs. Then we will see the problem with our approach. We will see that we will not always get the minimized DFA. Then how do we minimize that DFA is what we are going to understand in that example. We will discuss the minimization algorithm, and then we'll apply that algorithm on 3 or 4 examples, right? So this is roughly the agenda of this session is, right? So let's start directly with the question on deterministic finite state automata. So let's read out the question. The question says, construct a minimal DFA. Construct a minimal DFA. Just a second. So the question simply says construct a minimal DFA which accepts set of all strings over sigma equals to a comma b. So your sigma is still same. That means sigma star is basically a comma b star. Your strings are subset of sigma star such that a is never followed by a bb. So that what does it mean? That whenever you get an a, it should not have any bb in its follow, right? It should not be followed by a bb. This should be avoided, right? So this is basically the DFA which we want to make. Why I'm taking 1 or 2 more examples is to give you the motivation for minimization, right? So let us try to understand that. I'll give you some time, maybe 3 minutes to solve this because it's a bit difficult question. So let me give you some 3 minutes to solve this, and then I will solve it for you guys. If you can solve it faster, then it's also good. Then we'll discuss the solution faster. You have to tell me the number of final states as well as the number of states. Right? You have to tell me the number of final states as well as the number of states in this DFA. Yeah. What should be the answer, guys? We have the number of, you have to tell me the number of final states as well as the number of states in this example. Yes, can you guys be a bit faster in replying to this? Okay, I think enough time has been given. Let us discuss the solution now. So, let's see what this question is expecting us to do. It says that construct a minimal DFA which accepts set of all strings over sigma equals to a comma b such that a is never followed by a bb. That after an a you should not find a bb. So what's the first step in general that we have discussed? What's the first step in general that we have discussed multiple times? That you should write down the language. So this language contains epsilon because epsilon does, in epsilon a is never followed by a bb, so epsilon is a part of the language. I can say b is a part of the language, b is a part of the language, any number of b's is a part of the language. Now if I add a, if I have a, then it should not be followed by a bb. Single b, single a is okay, single a is okay, a is okay, a b is okay, a b b is not okay. That is the only problem. And similarly, so there can be many other strings. You can have AB, and then AA, and so on and so forth, which definitely satisfies this condition that A is not followed by a BB, right? So this is briefly the language that you have, right? Now, when you have this language, what you have to do is, let us start making the DFA. We know that epsilon is a part of the language, so we accept it. The initial state becomes our final state also. Now, if B keeps on coming, we will definitely keep on accepting, there is no issue. As long as B's are coming, we are okay because we are accepting it, right? Now, if an A comes, then also we are accepting, there is no issue. If this, after that, if a B comes, then also we are accepting, there is no issue. But after that, if another B comes, then we are having a problem. We go to a dead state where we'll stay forever. Why we are doing this? Because Here A has been followed by a BB. What does that mean? That means that this state has been rejected. This state needs to be rejected, right? So here A is being followed by a BB. That means we need to reject this state, right? So that means we go to a dead state, and whatever comes after it does not matter to us at all, right? That makes sense? Now what might happen? Well, let's see. Let's complete this DFA. We have completed the DFA for the smallest string in the language, and over here ABB is also getting rejected, right? Now, what if A keeps on coming? What if A keeps on coming? In this case, it's fine. If A keeps on coming on this state, AA is acceptable, so we'll stay over here only, right? Now, at this state, we know what needs to be done on AB. At this state, we know what needs to be done on B. We need to check on A. On this state, we have already done it on AB. On this state, we have already done it on AB. Now, what needs to be done? What needs to be done when an A comes on this state? Now, let's see. AB is acceptable to us, right? AB is acceptable to us. Now, after that, if another A comes, we are in a situation that we have got an A, and now it should not be followed by a B. So, we'll go back. Because if I stay at the same state, then strings of the type AB might also be rejected. Like for example, AB comes and then another A comes and a B comes, this will be rejected, which should not be rejected. So we have to come back to still accept AB, AB. So for example, A comes, B comes, another A comes, and then B comes, this is okay. But after that, if another B comes, then it is a problem because A should not be followed by a BB. That is the problem, right? Are you getting this point? So A should not be followed by a BB. That is a problem. A followed by a single B is not a problem. But if I put an A loop over here, then this A will be followed by a single B and it will be rejected. No. What should I do? A should be taken over here. Then if a B comes, it's okay. But another B comes, this is not okay. So therefore, this will be the DFA that you will get. Now, have I written the transitions for AB? Yes. Have I written on this state the transitions for AB? Yes. On this state on AB? Yes. On this state on AB? Yes. Yes. So I think this is briefly the DFA that you get. This is your DFA, right? And right. So now, if we see this DFA, can you tell me the number of final states that are 3? We have 3 final states in this DFA, and the total number of states that I have is 4. Now, what percentage of states is final? That is 3 by 4 into 100, which is nothing but 75% of my states are final states. Right? Is it making sense to everyone? So this is how we will make the DFA for this example, right? Yeah. If you have any doubts, please ask me. Right? So what is important in this question is, if you on A, you have to come back. You cannot stay on the same state. Although AB, A is accepted. You could have accepted on this state also. But that would lead to rejection of the string in which A is followed by a single B. How? AB is accepted. After that, if another A comes, if I keep the loop here, after another B, it will be rejected, which is not the case. It should be rejected by A followed by 2 Bs. So I'll go to a state which will check it for 2 Bs, which is this state, right? So the answer to this question will be 3 final states out of the total 4 states, and but what percentage of states are final? That is 75% of the states are final, right? Now this example is okay, and if we see this example, every state has a different behavior. Every state has a different behavior. So for example, if you see this state, this is one of the final states. On B, it remains on itself, and on A, it goes to the next state, which is also a final state. And this state on A remains on itself, and B, it goes to the other state. So this behavior is different, right? Now, this state has a completely different behavior. On A, it goes back to one of the final states. On B, it goes to a dead state. Again, it has a different behavior. We cannot merge any states. So what I'm trying to do is, can I do any minimization in this example? That is what I'm trying to discuss. Now, in this state, this is a dead state. We cannot merge it with any state because on AB, it remains on itself and can never lead to the final state, right? So what I'm trying to motivate is, once you have drawn the DFA, now you can check that whether are there any set of states which are having similar behavior and we can merge those states. In this example, where there is no, we do not have any such case. Let us see one example where we'll have such a situation wherein the 2 of the states have similar behavior and we will end up merging those 2 states. And then we will see that yes, minimization might be done, might be possible to be done in certain situations. And is there an algorithm for doing the same so that we get the minimized DFA, minimal DFA, right? So let us try to understand it through another example. Here I am saying that construct a minimal DFA which accepts set of all strings over sigma equals to a comma b such that every a is followed by a bb. Here every a is followed by a bb. Over there, what the example said, every a is not followed by a bb. Here every a is followed by a bb. You have to tell me the number of states as well as the final states in this DFA. So tell me the number of states as well as the number of final states in this DFA, right? You have to tell me the number of states as well as the number of final states in this minimized DFA. This is also a very good question. So let me give you 3 minutes to solve this, and then we will discuss the solution. What should be the number of states here? Yes, what should be the answer, guys? Okay, so time is up. Any answers, guys? Okay, so let me make the DFA now, and then let's see what can be done in this DFA. Can we do better in this DFA? Let's go with the ideal approach, and then we will see what can be done and what cannot be done. Right? So what I'm saying is every A is followed by a BB. So let us write the language. First of all, epsilon comes in this language. Then we have single B is in the language, double B is in the language, triple B is in the language, and so on and so forth. Any number of B's are there in this language. Then single A is there in the language. Every A has to be followed by a BB. So single A is not there in the language. Every A has to be followed by a BB. If an A comes, you are must to have a BB. Now, if an A comes, then BB is must. Then another A comes, another BB is must. So similarly, A comes, BB can come, another B can come. Then again A comes, a BB has to come, and then BB can come. So and so on and so forth. This is again an infinite language. We need to draw the DFA to get it accepted, right? So let's try to understand how we can make this DFA, right? So let's try to understand how we can make this DFA. So as epsilon belongs to this language, so starting state will be the final state for sure. So let us try to make the starting state as final state. And now when B comes, we are still accepting it. Any number of B's are acceptable, so we have kept them here. Now what if an A comes? If an A comes, it has to be followed by a BB. Then only we are going to accept it. Otherwise, we are not going to accept it. What we get is ABB. So ABB accepted. Therefore, I have made it like this. Now let's try to draw the other transition so that we can complete the transition table. We can complete the transition table and we can complete the transition function. That is, for every combination of Q cross sigma, we have to tell what will be the state on which we have to go. For every combination of Q cross sigma, we have to do this, right? So now, once an A has come, it has to be followed by a BB. If it is not followed, so for example, after an A, if another A comes, this is a problem. You go to a dead state and then you remain there forever, right? And then you remain there forever. I think it might not be visible. Let me cross check. Okay, so let me make it a bit above so that it is visible. I hope at this height it should be visible. So let's say this is also, let me redraw. If an A comes after an A, this is not followed by BB, so you will remain at a dead state and you will stay there forever. This is not the final state, right? I hope this is visible now, right? Yes. So now this is one thing. Now at this state, after getting an AB, A has come, after that 2 B's has to come. If only 1 B has come and after that and another A comes, again you are going to a dead state. The same dead state can be used because one dead state is enough to say the rejected case, right? So A. So after AB, if another A comes, you are again going to a dead state, which means that you are not going to accept it, right? So now let us see whether all the transitions are complete. And on this state, once you have got again, so let's see whether all the transitions are complete or not. On this state, we have told what happens on A, what happens on B, what happens on A, what happens on B, what happens on A, what happens on B, what happens on AB. Now on this state, if you get another B, so this is just like, okay, we can have another B over here. We can have another B. Because any number of B's is not a problem. If I'm accepting and after that, for an A, if I've got an A, B, B, that means that after that if another B comes, another B comes, another B comes, no issues because there is no condition on B's. All the conditions are only on A. Right? Are you getting this point? That every A has to be followed by BB. There is no condition on B. Any number of B's can come anytime, there is no issue. Right? But once an A has come, it has to be followed by a BB. Then only we can have other things. Right? So now, at this state, if you see, A is followed by BB. Now, after that, if a B comes, there is no issue. But if an A comes again you have to do the same check. That is, this A also has to be followed by another BB. So therefore, you come back to this state which checks that whether A is followed by 2 BBs or not. So this is how the DFA will look like in general. Now the question comes that whether can we minimize this DFA and get a better DFA? Let's see the state behavior of every state and see if the two states are having similar state behavior, similar behavior on the input, then we can consider merging those states. Let's see. And that will give you the motivation for minimization. Let's try to see that through this example. Now let me take it to the next page. Let me take it to the next page. Oops. Now let us try to analyze this DFA now. Now what this DFA is doing? It is accepting the strings. It is an automata which accepts the language. Every A is never followed by every A is followed by a BB. That is basically the case. Let's see that again. Every A is followed by a BB. That's what is being done. Okay. So just a second, the slide came a bit before. Let me rescale it. Yes. Now let's see this. Now what is the case here? If you see the behavior of this state, let me name the states as Q0, Q1, Q2, Q3, Q4. Now Q4 is a dead state. It has no other state has this behavior, so therefore Q4 will be, we cannot merge Q4 with anyone. Now Q0 if you see, Q0 on A is going to Q1 and Q0 on B it remains on itself, and it is also the final state. And if you see the behavior of Q3, on A it is also going to Q1 and it is also on B it remains on itself, and it is also a final state. So can we observe that the behavior of the state Q1 and Q3 are almost similar? In fact, I should say they are exactly similar. Now, if their behaviors are exactly similar, why not we merge these two states? Why can't we merge these two states into one state and then try to find out the minimized DFA, the minimal DFA, which has lesser number of states and we cannot reduce it any further? Why can't we do something like this? Let's see. Now, so let's see. So one thing which is obvious is Q0 on B is going to itself, Q3 on B is also going to itself, and both are final states. Q0 on A goes to Q1 and Q3 on B also goes to Q1. So we can merge Q0 and Q3, and from Q2 itself on B will directly go to Q0. That will serve our purpose. Are you getting this point? Now, how to observe this thing? And if we observe this in Q1 and Q2, Q1 on B is going to a dead state, on A it is going to a Q1 on A is going to a dead state, on Q1 on B is going to Q2, which is not a final state. But Q2 on A is going to again dead state, but on B it is going to a final state. So we cannot merge these two states. They have a different set behavior, right? But in this example, if we see Q0 and Q3 are having the similar set behavior, because on both on A are going to Q1, on B they are remaining on themselves, which are final states. So let us merge Q0 and Q3, and on B let us directly send Q2 to Q0. So this is how we will get the new DFA. That is, let me copy this again if I can. Okay, might be tough if I paste it here. No. So let me what I will do is I will try to change to redraw it, let me say. So initially you have, as I said, Q0 on B it remains on itself and it is a final state too, and on A it goes to Q1, on B it goes to Q2, On B it goes to Q2. Now Q2, which I am suggesting is on B, it should directly go to Q0 instead of Q3, which is having a similar behavior to Q0. And on A, both of them on A will lead to Q4, which is a dead state. So this is basically what we have obtained now, is basically the minimized DFA, that is, it cannot be reduced any further in any way. That is, you cannot have lesser number of states than this DFA, that is minimized DFA. Or I should say it's minimal DFA. So in this case, we could observe the behavior with our eyes directly. We can observe this behavior directly in this case. But is there an algorithmic way through which we can do this merging process? That is what we are trying to understand. Here we can directly do this merging by looking at the individual behavior of the states, right? And this process can go on forever. So for example, right now I have merged Q0 and Q3. Now I have got this DFA. Again, the same thing can be done. Similarly, once I merge something, then again the same thing can be done to check the behavior of the states. Again, similar things can be done over there also. Now this process can go on forever, and it will be tough to stop that. Therefore, therefore it will be tough to. Instead, you can solve it when only one state is left. You can stop at that point. But again, that becomes very, very, very mechanical in observing the behavior in every state, in every DFA that you get after every step. So that becomes a bit difficult process. There is an algorithmic way through which you can solve and get the minimized DFA, right? So let us try to understand the algorithm. Let us apply, first of all, understand the algorithm. When we'll apply the algorithm on this example, and then we'll see that whether we are getting this thing or not. Even on this state, if I check right now, that is the state behavior same? So KF Q4 is a dead state. It cannot have the similar state behavior with any state. Q0 is the accepting state, final state. It cannot have the similar state behavior because only one accepting state is there. Now Q1 and Q2, Q1 on B is going to Q2, which is non-final, but Q2 on B is going to a Q0, which is final. So they also have a different set behavior, right? They also have a different behavior on input. So therefore they cannot be merged. So this is how we can think, and we keep on thinking until we reach to only one state. But this process will be very, very mechanical. Can we do something better so as to get ascertained that what we have done is correct or not, right? So let us try to understand the minimization algorithm, and then we'll apply that same minimization algorithm on our example that I have given, and then we will apply it on some other examples. Now let us try to understand what is minimization of DFAs. How do we do it? So first step, which is very, very important, is to remove all the unreachable states. What are unreachable states? Which cannot be reached, which do not have any incoming edge into them, right? But again, it might be single state on which there is no incoming edge, or it may be group of states on which there is no incoming edge. And therefore, it is always advisable to directly draw the DFA and see any unreachable state is there or not. Directly, do not by looking at the transition table. You might not be able to tell always that the given state is an unreachable state or not, or given set of states is an unreachable set of states or not. Maybe in case of just single state, you might be able to find, but in case of multiple states which are unreachable, in that case it's better to draw the DFA, then only you will get to know which set of states are unreachable. So when you are saying remove all unreachable states, what does it mean? That any set of states which are unreachable, you have to remove all of those states. Are you getting this point? All the states which are unreachable, you have to remove all those set of states. If that is single state, you can directly look at the transition table and directly tell that, see, this state is not reachable because there is no incoming edge on that state. Therefore, that is unreachable. But by looking at the transition table, you will not be able to tell if there is a set of states which are unreachable. In that case, some of the states might be reachable also through that set. but that set entirely is unreachable. So it's better to draw the transition diagram. It's better to draw the automata and then try to finally tell that what are the states which are unreachable. Otherwise, this does not make any point. So therefore, for checking unreachability, always make the DFA for checking. Yes. Now divide the states into two sets. One is final and other is non-final states. So we divide the states into two sets of states, right? One set will be final states, other set will be non-final states. These states and sets thus obtained are zero equivalent. Now you will make two sets of states, one which will contain final states, other set will contain non-final states, and these two sets which you have obtained now are called as zero equivalent states. So what do you mean by zero equivalent? Without accepting any input, they are having the similar behavior. Those which are final, they are accepting that. Those which are not final, they are not accepting it. So without accepting any input, what is their behavior? This is known as zero equivalent. Now next thing is split the states which do not have. So once you have got the zero equivalent states, now the next task is to find one equivalent states. That means that the states which have the similar set behavior on accepting one input alphabet, right? So split the states which do not have the same set behavior on all the inputs. On all the inputs in sigma, right? So for example, my sigma is A comma B. So all those states which have the similar behavior on all the inputs, either A or B, both A and B, they will be coming in the same set. We will not be separating them. But if they have different behavior, we will separate them. Which do not have the same set behavior, they needs to be separated. Which have the same set behavior, they will remain together. Right? Now keep on splitting. What you have to do? You have to keep on splitting until the states stabilize. The states thus obtained are n equivalent, right? So if you are doing this process, you keep on doing this process. Once you get some set of states, again apply the same process. Once you get another set of states, you again apply the same process, and so on and so forth, right? So this you need to do. Keep on splitting until the states stabilize. The states thus obtained are known as n equivalent. The states thus obtained are known as n equivalent states. So what do I mean by state? Unless the state stabilize, that means no further splitting can be done. If at level k you are having certain sets, at level k plus 1 again you are having the similar sets. That means that you cannot do, even if you keep on going applying inputs, you are going to get the same set. So that means that they are having similar set behavior. Now if the set behavior is similar of kth one and k plus 1th one, that means they are equivalent. What you have got is, if you keep on applying this again and again, what you are going to get? You are going to get the same set. So that means the sets have stabilized, and whatever will be the length of the input, either 0 length, 1 length, 2 length, 3 length, up to n length, for any n length, they are having similar set behavior. So now we can get the final minimized DFA. Right? So let me read it out again. Let me read it out again. What do I mean? Keep on splitting the states. Keep on splitting until the set stabilize. The states thus obtained are known as n equivalent. Right? Because how we have reached it? Because we will reach it there. For example, kth split and k plus 1th split, they are giving exactly the same output. That means for any value of n, they will have the similar set behavior. So therefore, they are known as n equivalent. Right? Now, once you have done this, now what is left? Now you have got the final set of states. What is the quintuple? What is the quintuple? The quintuple was q sigma delta q naught and f. What you have done is, sigma you already know, q you have found out now. After applying the minimization algorithm, you have already found out q. How many final states you have? How many states you have now? Now what is left is how to find out delta, how to find out q naught, how to find out f in the minimized DFA that we have got. Right? In the minimal DFA that we have got. So the transitions are obtained from the original DFA. Keep on looking at the original DFA, you will get the transitions. The initial state will be the one which contains the start state of the original DFA, which contains the start state or the initial state, of the original DFA, right? And what will be the final states? The final states are the ones which contain any of the final states of the original DFA. So here the word any is a catch, any of the final states of the original DFA. Right? Any of the final states of the original DFA will be the final state. So those states which contain any of the final states of the original DFA are known as which contains any of the final states of the original DFA. Original DFA, then only we will say it as it is a final state in my new DFA. Right? So is it making sense? Yes. So now let us try to apply it on the example that we had earlier and then see whether we are getting this or not. If we are getting this, then we are done. That means we have understood the algorithm well and it is working perfectly fine. And then we apply this algorithm on some few more examples to understand this concept in a better way. Right? So let us try to take this picture on some other page. Right? So this is our DFA which we want. This is what we have. Now let's see this. So what is the first step? Remove any unreachable state. Is any state unreachable here? Let us try to find out. This is reachable, this is reachable, this is reachable, this is reachable. No state is unreachable here. That is very clear. Now the next step is to divide the states into two sets of states. One is final states, another is a set of non-final states. Now the final states are Q0 and Q3. And the non-final states are Q1, Q2, Q4. So this is one thing that we already know. Q0 and Q3 are final states, Q1, Q2, Q4 are non-final states. If we know this, now we have to find out what is the set behavior. Now there are two elements here. Let's find out their set behavior first. Now Q0 on A goes to Q1. Q3 on A goes to again Q1. So they have the similar set behavior. Now Q0 on B goes to Q0 itself. Q3 on B also remains on Q3 itself. So they have the similar set behavior. Q3 on B also remains at Q3. So they have the similar set behavior. There is no need to separate these. On A, they are both going to the different set. That is Q1, Q2, Q4. And on B, they are remaining in the same set, that is their own set, so therefore they have the similar set behavior. So again, this is important to understand, the set behavior has to be the same, the state behavior is not required to be the same. When I say the set behavior, that means they should go to the same set, not to the same state, which is very important. Right? Let me show this point very clear to you. Split the states which do not have the same set behavior, not the state behavior, which is very, very, very important to understand. Now let's talk about Q1, Q2 and Q4. Q1 on A goes to Q4. It remains in the same set. Q1 on B goes to Q2. Again the same set. Now Q2 on A goes to Q4. Q2 on A goes to Q4. Q2 on B goes to Q3. Now this Q2 has a different set behavior than Q1. So therefore Q1 has to be separated. So we already have Q0, Q3. Now Q1 is one set, Q2 has to be separated from this set because Q1 and Q2 are having different set behavior. Why? Because Q1 on A is going to Q2, Q2 on A is going to Q4. Q1 on A was going to Q2. So Q1 on A was also going to, just a second, Q1 on A, let me recalculate it. Q1 on A is going to Q4. Q1 on A is going to Q4. Just a second. Yes. Now let's try to find out the behaviors of Q1 and Q2 again. Q1 on A goes to Q4 and Q2 on A goes to again Q4. So with A they have the same relationship. With B, Q1 on B goes to Q2. So on Q1 on B is going to Q2 and Q2 on B is going to Q3, which is a final state. So again the set's behavior is different, therefore I have separated Q1 and Q2. So their set behavior is different, therefore I have separated Q1 and Q2, because on A they are remaining in the same set, but on B, Q1 is going to Q2, which is in the same set, but Q2 on B is going to Q3, which is not in the same set. Are you getting this point? Right? Now let's see the Q4's behavior. Q4 on A is going to A and B, it is going to both on itself. On A and B, it is again remaining on itself. Now, is this set behavior similar to Q1 or Q2 in any way? Q1 on A is remaining in the same set, Q2 is remaining in the same set, Q4 is also remaining in the same set, there is no issue. On B, Q2 is also remaining in the same set, Q4 is also remaining in the same set, the Q2 and Q4 has a similar set behavior. How? Let me reiterate this point. Q2 on A is going to Q4, Q2 on B is also going to Q2 on A. So first of all, we have to check the set behavior on A. So Q2 on A is going to Q4, Q2 on A is going to Q4, Q4 on A is again going to Q4. That's it. Both are in the same set. Now Q4, Q2 on B is going to Q3, which is a final state. So we cannot merge these two guys. Just a second. Let me recheck the behavior. Let us recheck the behavior together. Let's see. Q2 and Q4, let's see whether we can have Q2 and Q4 in the same set. Then we'll check whether Q1 and Q4 can come in the same set or not. Let's see that again. Q1 on A is going to Q4. Q1 on A is going to Q4. Q1 on A goes to Q4 and Q4 on A also goes to Q4. So they are having the similar set behavior. Now, Q1 on B goes to Q2, that is this same set. Q4 on B also remains on Q4, which is the same set. So Q1 and Q4 are having the similar set behavior instead of Q2 and Q4. Just a second. So Q1 and Q4 will have the same set behavior. Right? Now let's check for this one. Q2 has a different behavior from both of them, because what is happening, Q1 and Q4 both on A. Q1 goes to on A, it remains on Q4. Q4 on A remains on Q4. So both are on A, they both are going into the same set. Q2 also on A goes to the same set Q4. That is the same set Q1, Q2, Q4. But it is different on B with Q1 and Q2. So therefore Q2 has been separated. Why? Because Q1 on B, if you see, you are going to Q2. Q1 on B is going to Q2. That is the same set. Q4 on B goes to Q4 itself. That is the same set. So Q1 and Q4 are together. But now, if I do it on Q2, Q2 on B is going to Q3, which is not the same set. So therefore Q2 has been separated. Now these two, this set initially that we got is basically zero equivalent. What we got here is zero equivalent. Zero equivalent. Now these two are one equivalent. These three which we have got is one equivalent. That means they have the similar state behavior. They have the similar set behavior. That means they have the similar set behavior without accepting any input. They have the similar set behavior after accepting one input. Now let's find out the set behavior on accepting two inputs. That is one more input. Let's see what happens. So here we don't need to check this because it's already separate. We need to check this and this. Let's check. Q0 on A goes to Q1. Q0 on A goes to Q1. Q0 on A goes to Q1, and Q3 on A. Q3 on A also goes to Q1. So they have the similar set behavior. At least on A. Let's check on B. Q0 on B goes to Q0. Q3 on B also goes to Q0. So they have the similar set behavior. They will remain intact. We are not going to separate them. Now Q1 and Q4, let's check it out. Q1 and Q4 we have to check. Now Q1 on A. Q1 on A is going to Q4, and Q4 on A is also going to Q4 itself. So both are remaining in the same set on A. Both are in the same set on A. At least on A they have the similar set behavior. Now let's try to find out what happens if a B comes. Now Q1 on B goes to Q2, and Q4 on B goes to Q4 itself. So they have a different set behavior on B. Right? So we will again separate them. They will again be bifurcated. So what we will get now is Q0, Q3, Q1, Q4, right? Q0, Q3, Q1, Q4, Q2 is what we will get. Again, are you getting the point or not? Is it visible? So I think some of it is gone. So let me rewrite it. So just to reiterate it, I'll write it on the other side. What I'm doing is I have separated Q1 and Q4 because on B, Q1 is going to Q2 and Q4 is remaining on itself. So therefore we need to separate them. They have a different set behavior on two length strings. Therefore they are two equivalent, because after accepting one input, I took one more input. So the length of the string becomes 2. Right? So Q4 gets separated. So let me write it down on the other side since it's not visible. So what it will become? It will become Q0, Q3, Q1 separately, Q4 separately, and Q2 separately. This is what we will get. Alright. Now let's try to find out again whether we are again able to split it or not. Now nothing can be splitted from Q1, Q4, Q2 since they are singletons. Now let's see about Q1 and Q3, Q0 and Q3, which are to be merged. Now Q0, let's see, Q0 on A is going to Q1, Q3 on A is also going to Q1. Both are going on Q1. Now Q3 on A, Q3 or Q0 on B, Q0 on B remains on itself. Q3 on B also remains on itself. So they are having the similar behavior. Both of them are having the similar set behavior. Both on Q0, on A are going to Q1, on B they are remaining in themselves. They are remaining in the same set. So therefore they cannot be splitted now. When we have to split, when they do not have the same set behavior, they have the same set behavior. So the next state that we are going to get, will be Q0 will be Q0, Q3, Q1, Q2 and Q4. So now let us see over here, this was the 2 equivalent. Now this was 2 equivalent. Now what we get now is 3 equivalent. Now 2 equivalent and 3 equivalent are same. Now if we keep on applying this also till n, for any n they are going to give you the same result. So they will become n equivalent also. So when any two consecutive equivalents are equal, then we can declare that they are n equivalent also, because if you keep on going on, you are again going to get the same sets. So therefore they will be n equivalent also. Right? So these are n equivalent also in this case. So what we get now is Q0, Q3, Q1, Q2 and Q4. This is what we have got now. Right? Now let's try to see how we will. Now these are the states that we are going to get. That means Q0 and Q3 are going to be one set. Q2 will be a different set. Q1 will be a different set. Q4 will be a different set. So out of 5 states, we now get 4 states. Q0 and Q3 needs to be merged. So let us now let us now understand the merge process. So right now what is being suggested is we have got the states. Now we have to check the transitions as well as the initial state as well as the final states. Let's see. So what will happen is Q0 and Q3 needs to be merged. Then we will have Q1. Then we will have Q2. Then we will have Q4. Now how will we get the transitions? The transitions will be obtained from the original DFA. Q0, Q3 on B. Now Q0 on B goes to Q0, Q3 on B goes to Q0. Both are going to the Q0, Q3 only. So on B will remain here. On A, both of them are going to Q1. So we will go to Q1. On A, on B, Q1 is going to Q2. Right? So on A, on B, Q1 is going to Q2, and on A, it is going to Q4. Q4 is going to AB itself on AB. Now Q2 on A is going to Q4, and on A and on B it is going to Q0, Q3, which is nothing but Q0, Q3 now. On A, sorry, A, B, B. Yeah. So on B it is going to Q2 on B is going to Q3, which is not now but nothing but Q0, Q3. Right. So this is what we will obtain. Now we need to find out the initial state as well as the final state. The initial state will remain the same, which contains the initial state of DFA or the original DFA. Original DFA's initial state was Q0, so Q0, Q3 will be our initial state also. Now the final states will be all those states which contain any of the final states of the DFAs, that is Q0 or Q3. So therefore Q0, Q3 becomes our final state. So this is a state which contains any of the final states. No other state contains any of the other final states. So for example, in this state does not contain Q0, this state does not contain Q0, this state doesn't contain Q0. Neither of these states, no, and otherwise also Q3 is also not there, Q3 is also not there, Q3 is also not there. So therefore this is the only state which will be our final in this case. Right? So therefore what we are going to get is this minimized DFA. Now this is an algorithmic approach through which we can minimize any DFA which is given to us in the question. Minimized DFA or the minimal DFA. That is, we cannot reduce it any further. Right? I hope this is clear. Right? So what you have to do? What are the steps? First of all, you have to remove all the unreachable states which are unreachable, that cannot be reached. Then divide the states into two sets. Final and non-final, these are zero equivalent. Split the states which do not have the same set behavior on all the inputs in sigma. These states thus obtained are one equivalent. Keep on splitting up unless your state sets stabilize. That means they will become n equivalent. For any value of n, they will be equivalent. So that means kth and k plus 1th equivalent should be same. Then we'll say they are also n equivalent. And once you have done that, you find out the transitions from the initial DFA, initial state. Whatever is initial in the original DFA, all the states and the state which contains that initial state will be the initial state in the new DFA that you have got, the minimized DFA, the minimal DFA that you have got. Now what are the final states? The final states are those states will be final which contains any of the final states of the original DFA. This is how you do it. So you have found out the Q first, then you found out transitions, then you find out initial state, then you find out the final states. Now what is left is sigma. Sigma is already known. That is A, B. So this is how you carry out the process of minimization. Let us take one more example which you guys will solve in the next 3 minutes, and we will discuss the solution. Solve it in the next 3 minutes and then we'll discuss the solution. Wait. This guy is how many states will get in the minimized DFA. So this is basically the transition table which is given to you. Okay, the time is up. Let us try to solve it now. Let us try to solve it now. So what is being done is, what is being talked about is the minimization of DFA. And first step will always be to find out unreachable states. And as I already discussed when I discussed the algorithm in detail, that for finding out the unreachable states, always make the DFA. Do not directly look at the transition table and try to comment upon that some state might be unreachable, because it's not appearing in the transition table. Maybe in the transition of any other state, right? So that should not be the way, because if it is only one state which is unreachable, then this way we can work. But if it is a group of states, then somebody might be in that group, might be reachable through through someone which is in its own set, through someone which is in its own set, which is unreachable completely. Are you getting my point? So I'll take that example to make that point very clear to you when the time comes. But let us try to solve this example first, right? So what I'm trying to say is, if there is only one state which is unreachable, then you can look at the transition table directly and then say that, see, this state is unreachable because it's not coming in the transition of any other state. But if a group of states is unreachable, then it might become a problem to directly use it like this. Why? Why? Because in that unreachable set, some of the states might be reachable from each other, but that set in itself is unreachable. That is what I wanted to say, right? We'll see some example, one of that examples, to show you that why we should not use directly the transition table approach, right, in finding out the unreachable state. Now, over here in this example, if you see, let's try to make the DFA first. So Q0 is my initial state as well as the final state. On A, it is going to Q1. On B, it is going to Q2. Now, Q1 on A goes to Q1 itself, and on B, it goes to Q3. Right? And then Q2 on A goes to Q1, Q2 on A goes to Q1, Q2 on B goes to Q2, Q3 on A goes to Q1, Q3 on A goes to Q1, Q3 on B goes to Q4. I have not written on what is the transition. Q1 on B was going to Q3. Q1 on B was going to Q3, and Q3 on A was going to Q1. Q3 on B was going to Q4. Right? Now, Q4 is your final state, not Q0, right? Q0 is just the initial state in this case. So Q4 is your final state here. So Q0 is your initial state. Now Q4 is my final state also. Is my final state. Q4 on A is going to Q1. Q4 on B is going to Q2. So this is what we have. Q4 on B is going to Q2. So let us just cross check whether we have made the right transitions or not in the transition table. So what we are saying is Q0 on A, Q0 is our initial state, Q0 on A is going to Q1 and on B it is going to Q2, right? Now Q1 on A is going to Q1 and on B it is going to Q3. Q1 on A is going to Q1 and Q1 on B is going to Q3, right? Now Q2 on A is going to Q1, Q2 on B is going to Q2, Q2 on B is going to Q2 itself. Q3 on A is going to Q1 and Q3 on B is going to Q4. On A to Q1, and B to Q4, very good. And Q4 on A is going to Q0. Q4 on A is going to Q1. Q4 on A is going to Q1 and on B it goes to Q2. So it's Q1. On A it is going to Q1. Q4 on A is going to Q1. So Q4 on A goes to Q1 and on B it goes to Q2. This is what is given. Now let us try to solve it. But before we do that, let's find out the unreachable states. So what are unreachable states here? Q1. If we see Q1 is reachable, Q2 is reachable, Q3 is again reachable, Q4 is also reachable. So there is no state which is unreachable here. We can directly apply the approach. So initially we'll have two set of states. That is Q0, Q1, Q2, Q3 and Q4 will come separately. This is basically zero equivalent. Right? Let's try to find out one equivalent wherein we will try to provide one input. So we'll try to see the set behavior on getting one single input, right? On all input alphabets, we'll see that what happens. So Q4 is already separate, so we don't need to worry. What we need to worry is what happens with Q0 on A. When Q0 has an A, Q0 on A goes to Q1, Q0 on A goes to Q1, Q1 on A goes to Q1 itself. So they have the same set behavior, on A at least. Now Q2 on A goes to Q1, again same set behavior. Q3 on A goes to Q1, again the same set behavior. All of them are having same set behavior on A. Let's see on B what they have. Now Q0 on B goes to Q2. But Q1 on B goes to Q3, again same set behavior. Q2 on B goes to Q2, again same set behavior. But Q3 on B goes to Q4, which is a different set behavior. So therefore Q3 will be separated. So what we will have afterwards? We'll have Q0, Q1, Q2, Q3 separated, and then Q4 will also be separated. So these two states, these three sets that we have obtained are basically one equivalent. They are basically one equivalent. Now let's try to find out the set behavior in this case. What will be the set behavior in this case? Let's see Q0 on A. Q0 on A goes to Q1. So all of them on A all goes to Q1 only. So therefore through A they will never have an issue. They will have the same set behavior. Let's see B. Q0 on B goes to Q2, Q1 on B goes to Q3, different set behavior, and Q2 on B goes to Q2 itself, same set behavior. So Q1 has a different set behavior. We'll separate Q1 out of Q1, Q0, Q2. So what we will get is Q0, Q0, Q2, Q1 gets separated, Q3 was already separated, Q4 was already separated. Right? So these two states that we obtained, these four sets that we have obtained are basically 0 equivalent was this one equivalent, and this is now 2 equivalent. That on two length inputs, they will have the similar set behavior. Right? Why we separated Q0 and Q3? So Q0 on B is going to Q2 and Q3, Q1 on B was going to Q3, a different set. Q2 on B was going to Q2 itself, that is the same set. So Q0, Q2 needs to be merged. Q1, Q3, Q4 will be separated. Now let's see Q0, Q2 behavior again. And if they stabilize, then we do not need to go any further. So Q0 on A goes to Q1. Q0 on Q1, Q2, Q3, Q4. So Q0 on A goes to Q2, Q0 itself. Q0 on A goes to Q1. Q0 on A goes to Q1, sorry. So we should write it as Q0 on A goes to Q1. Q0 on B, Q1 on Q2 on B also goes to Q1, same set. Q0 on B goes to Q2, same set. So this is E. So what I am suggesting is Q0 on A goes to Q1, Q2 on A also goes to Q1, same set behavior. Now Q2, Q0 on B goes to Q2, Q0 on B goes to Q2, and Q0 on Q2 on B also goes to Q2. So again the same set behavior. So now they are not separated any further. So this 2 equivalent is equal to the 3 equivalent. So therefore we can stop here. For any value of n, they will be equivalent. For any input, they will be equivalent. Right? So therefore Q0, Q2 needs to be merged with Q1, Q3 and Q4 will be a separate state. So we only need to merge two states, that is Q0 and Q2. And if I merge these two states, I will get the minimal DFA. Right? So how do we do that? What should I do is I will try to take this on the next page so that I can make the changes over there itself. Plus, I made a copy of this slide and then this one. Now what I want is Q0, Q2 needs to be merged, right? So I already know Q0, Q2 needs to be merged. So I will draw the DFA over here. I'll remove this DFA that we already have. Let's find out the new DFA here. So that means that you will have Q0, Q2 as one state now. And since Q0 contains the initial state, therefore Q0, Q2 will be your initial state. Then you will have one state as Q1. So Q1 is already there. Q3 is already there. Q4 is also there. That's it. Now let's try to draw the transitions. Now which one will be the final state? Q4 will be the final one because it is the only state which contains any of the final states of the original DFA. So now Q0, Q2 on A goes to Q1. Q0, Q2 on A goes to Q1. Q0, Q2 on B goes to Q2. Q0, Q2, Q0 on B goes to. So now we have to find out first of all Q0, Q2 on A. So Q0 on A goes to Q1 and Q2 on A also goes to Q1. So therefore they together goes to Q1. Now Q0 on B goes to Q2 and Q2 on also B goes to Q2. They will remain on themselves. Now Q1 on A goes to Q1. Q1 on B goes to Q3. Q3 on A goes to Q1. On B goes to Q4. Q4 on A goes to Q1. And on B goes to Q2. Q2 is this state. Q0, Q2. So this is how your DFA should look like afterwards. Right? Yes. Right? So this is how we solve such questions. Right? If the minimization questions comes, you have to make the original DFA first so as to find out any unreachable state. If there are no unreachable states, that's great. You can just simply go like this. If there is an unreachable state, you will remove that unreachable states. That's it. Right? So let's do one more example to understand this concept better and then try to see what exactly happens. Let's see this example. So let me set a timer for 3 minutes for you guys to solve this. Maybe 2 minutes timer for you. Okay, I think enough time has been given. Let us try to solve it faster. So now earlier examples I solved slowly so that you understand the concept. We'll try to do these examples faster. Let's see. So now we have 4 states over here, Q0, Q1, Q2, Q3. Now if you see this transition table itself, you can see that Q3 cannot be reached because on the right, on any transition, in none of the transitions Q3 is coming. Right? But I told you do not use this as the step because there might be a set of states which are unreachable and they might be reachable from themselves, but entirely that set is unreachable. Right? So therefore, I will again make the transition table, transition diagram, that is the DFA. I'll make that so as to ascertain that yes is only Q3 unreachable. Right? So let's see that. Although from this table itself we have got to know that Q3 is unreachable for sure. But let's try to draw the diagram so as to be ascertained about it. So initially we have Q0, and which is the initial state. Then we have Q0 on A goes to Q1. On B it remains on itself. On A it goes to Q1. Right, which is one of the final states. Now Q1 on A goes to Q2, which is again a final state. And on B, Q1 on B goes to Q1 itself. Could be. Right? On B, they are remaining on themselves. On Q0 on A goes to Q1 and Q0 on B goes to Q2. Now Q2 on A goes to Q1. Q2 on B goes to Q2 itself. Q3 on A goes to Q3 on A goes to Q1 or on B goes to Q2. Now if you see this, you can clearly see that Q3 is unreachable. You cannot reach Q3. So this entirely goes away. Now is Q1 reachable? Yes. Q2 reachable? Yes, definitely. So we'll only solve it for Q0, Q1, Q2. Right? Now when I solve it for Q0, Q1, Q2, how will I solve now? I know that Q0, so I have three sets now. Two sets, one is Q0 and Q1, Q2. Why Q1, Q2 in a separate set? Because they both are final. Let's see their behavior. Can we separate them or not? Q1 on A. Q1 on A goes to Q2. Q2 on A also goes to Q1. So they are in the same set. On A, they have the same set behavior. On B, let us try to find out Q2 on A goes to Q1. Q2 on A, we have checked. Q1 goes to Q2. Q2 goes to Q1. Now, on B, Q1 goes to Q1 itself. Q1 goes to itself. And Q2 on B goes to Q2 itself. So they have the same set behavior. So they can be merged here. They can be merged here. So 0 equivalent was this one, and 1 equivalent also comes out to be the same. That is Q0, Q1, Q2. So you can stop here itself. So how will you get the state transition diagram? So you will merge Q0, Q2 into one state. Sorry, Q1, Q2 into one state, and Q2, Q0 in a separate state. Now if that is the case, Q0 on A goes to Q1, which is Q1, Q2 now. On B, it is going to Q0 itself. Now Q1, Q2 on A goes to Q1, Q2 itself, and on B also it goes to Q1, Q2 itself. So that is, this set has become in itself one set, and this is the diagram. So this has been merged, Q1, Q2 has been merged. Right? So yeah. So on B, they are remaining on themselves. On A, they are going to each other, which are also final. So they have the similar set behavior. So therefore, they have been merged. Right? So it's tough to understand that way. So therefore, better to use this approach. Right? Yeah. So let us try to solve one last example, and then we'll end this session on minimization. And this example will prove you that it's better to draw the DFAs. Right? So as to find out the unreachable states. So let me quickly solve it for you guys. What you can observe here is, if you go by the unreachable state, if you want to find out unreachable states just by looking at the transition table, you will not be able to find out in this case, because in this case, if you see, Q0 is there on the right hand side, Q1 is there, Q2 is there, Q3 is there, Q4 is there, Q5 is there, Q6 is also there. Only by, if you apply this method, you will find that Q7 is only unreachable. But as I said you, if set of states are unreachable, then there might be a problem. Then this method of finding through the transition table might fail. It's better to always use which approach? Draw the DFA. Let's draw the DFA. So initially we have Q0. Q0 on A goes to Q1. Q0 is the initial as well as the final state. Q0 on A goes to Q1. Q0 on B goes to Q0 itself. Q1 on A goes to Q0. On B it goes to Q2. Q2 on A goes to Q3. Q3 on and Q2 on B goes to Q1. Q3 on A goes to Q3 and on B goes to Q0. Right? That's it. This much is fine. Now Q4 on A goes to Q3 and on B goes to Q5. Now Q5 on A goes to Q6. On B it goes to Q4. Now Q6 on A goes to Q5. Q6 on B goes to Q6. Q7 on A goes to Q6, and on B it goes to Q3. Right. Now if you see this diagram, Q1 is reachable, Q2 is reachable, Q3 is also reachable. But this entire section of Q4, Q5, Q6, Q7, this entire section is not reachable. You can neither come to Q4 nor come to Q5 from the initial state, right? And nor Q6 and nor Q7. So this entire section is going to be an unreachable section. So what you will be left with? Q0, Q1, Q3, Q2. So therefore it is important that you do not find unreachable states directly from the transition table, because over here you will only see that Q7 is unreachable. But if you draw the transition table, you will realize, transition diagram, you will realize that see, this entire set is unreachable because there was a set which was unreachable in the whole diagram, although they were reachable among themselves, but that was no use because they were unreachable from the initial state. So therefore it's better to draw the transition table, because this was the point which I was trying to make very clear since the beginning. So this example justifies, clarifies that point in a very proper way. You can go back to what I said in the beginning and then come back to this example again to understand this very clearly. Right? So now what are the states that I have? Q0 is one state which is separated because this is the final state as well, and all other states are known final. Let us try to draw. Let us try to put them in one set. Now let us see their behaviors. Q1 on A goes to Q1 itself. On A it remains here. Q2 on A goes to Q0, so it has to be separated, it has a different behavior. And Q3 on A goes to Q3 itself. So basically, Q2 has to be separated, it has different behavior from these two. So Q0 is separated, Q2 has been separated. Now among Q1 and Q3 we have to understand whether they will remain same or not. We have to check B. So Q1 and Q3. Q1 on B goes to Q2, that is the same set. Q3 on B goes to Q0, again a different set. So again, therefore they will also be separated. You will have Q0, Q2 and then Q1 as well as Q3 separately. So you will have four states, that is Q0, Q1, Q2 and Q3. So the transition diagram will also look like the one which you have drawn. Everything remains intact. This part is removed. There is nothing which can be done after minimization. Only the unreachable states have been removed. Now why these are different? Because Q1 on A, because Q1 on A and B is remaining in the same set. Q2 on A is going outside while Q3 is remaining inside only. So Q2 has been separated from Q1 because on A it is going outside. Q3 has been separated because on B it is going outside. Even Q2, Q3 cannot be merged. Why? Because Q2 on A is going outside and Q2 on B it is going outside. So therefore they are also different. So therefore this is what you get, and the minimized DFA will be this much. This will be your answer. Right? So that's all about minimization. You can solve more and more examples to get a hand on these examples, to get very clear about these examples, right? And I hope the point which I wanted to make is very, very clear to you. The DFA that you obtain after drawing the DFA might not be the minimal DFA. That means you might be able to further reduce the number of states in the DFA. So the approach which should be used is minimization approach, right? Because that is a generic approach. You should not directly look at the behaviors of the states. You should look at the behavior of the sets. That's all about minimization. Now, so if you see where do we stand right now in the foundation course, we are done with the introduction to TOC. We have introduced the subject. In this lecture, we talked about what is basically theory of computation and what are its various applications. In the next lecture, we talked about deterministic finite state automata. We introduced the concept, when we did various examples, then we did various advanced examples. So all these 4 sessions are done. And then minimization, we did minimization of the DFA, which is also which we completed today, is to find out the minimal DFA so that it cannot be reduced any further. The number of states cannot be reduced any further, right? Are you getting this point? Now, what are the other sessions? We'll meet Wednesday, that is 31st of May, on non-deterministic finite state automata. That is tomorrow from 4 p.m. to 5:30 p.m. we'll be talking about non-deterministic finite state automata. What is the need of non-deterministic finite state automata, why we make it, and then we will see certain examples on non-deterministic finite state automata. We'll also learn that how to convert an NFA into DFA, and we'll also see that every NFA is convertible to an equivalent DFA, right? So this is what we'll do in the next session. I hope to see you guys in the next session. Right? So that's all about this session. I'll see you tomorrow from 4 p.m. to 5:30 p.m. with non-deterministic finite state automata. Thank you, guys.